Mr. Rainsberg here, and we are looking at lesson 5.2a. It's the third lesson that we're dealing with probability, and this time we're going to focus on the different rules that deal with probability. And so before we go into that, we want to first look at what probability models are. And so we have right here an image of two die being rolled, and this right here lists out all the possible ways we could roll two die. And so here we have a 1 and a 1, a 2 and a 1, etc., all the way to rolling a 6 and a 6. And so if we want to find out what's the different sums we can have when we're rolling two die, we can make a visual of it when we have our probability model of drawing all the images. We could also use a tree diagram where you can see that we start off with just at this middle part here, and then it's going to branch off into all the different outcomes in the first event. And the first event is rolling the first die. And all the different outcomes are 1, 2, 3, 4, 5, 6, but each one of those outcomes, after I roll the first die and I roll the second die, I could also roll a 1 through 6 on the second die. And so each one of those outcomes have 6 branches going off of those as well. So we're going to dive deeper into tree diagrams in a future lesson. Right now, we're just going to focus on the idea of a probability model. And so right down below, you can see we have a table that lists out the different sums. And we want to know what's the probability of each one of those sums based off the model that we have. And I'm going to use the images down there of the die rather than the tree diagram. And so if I want to have to roll two die and I want to find out what's the sum of rolling a 1, well, that's impossible. If you have two die, you cannot roll a 1. So that means that event will never happen. The probability is 0. If I want to know what's the probability of rolling a sum of 2 with two die, that's right here. That's 1, and I have a total of 36 possibilities. So the probability is 1 out of 36. And we can keep going through this and see that if I want a sum of 3, that's right here, and that'd be 2 out of 36. If I want a sum of 4, I can get it with a 3 and a 1, a 2 and a 2, or a 1 and a 3. So that's going to be 3 out of 36. And so on if we work our way through all the different ways that we can have it. And if I do this, one thing I'm going to notice is that all the probabilities are between 0 and 1. Nice little trick right there with the 0 out of 36 there to see if you're paying attention. But one other thing to keep in mind is add the numerators together. 1 plus 2 plus 3 is 6, plus 4 is 10, then plus 5 is 15, then you have plus 21. And then I know 5, 4, 3, 2, 1 was the 15, so 21 plus 15, 36. All of these together add up to a sum of 1. And that's what a probability model should do, is all the probabilities should add up to a sum of 1. And we see that right here. So that's the first idea of what is a probability model. The next thing we're going to look at is some of the vocabulary and kind of introducing the notation with probability. So here we have an event is any collection of outcomes from chance process. The way we represent events with probability is we use capital letters. So we're going to look at either capital letter A, B, C, etc. And so for this example, we can take a look and we see that we have capital A represents rolling a sum of 5 on 2 dice. And capital B represents rolling a sum of greater than 10 on 2 dice. So we're going to focus on the notation with probability here. I mean, we could just quickly go back and look at the picture and count. So what we're going to focus on here is understanding how to write probability and communicate it properly. So if I want to figure out the probability of rolling a sum of 5 on 2 dice, I'm going to say that's the probability of event A. And I do that by doing capital P, parentheses, capital A. And so capital P, probability, parentheses, of whatever the event is. And what I can do is, instead of scrolling back and looking at the image, I have an image of it down here. There's only 4 ways to get a sum of 5 with 2 die. A 1 and a 4, a 2 and a 3, a 3 and a 2, or a 4 and a 1. So the probability is going to be 4 out of 36. Now, I'm not going to simplify that. When it comes to probability, let's just leave it alone. And the reason why is there's meaning to the fraction. There's 4 events out of a total of 36. So there's meaning to the numerator and there's meaning to the denominator. So I'm not going to simplify. That's the exception to the rule of mathematics when you're dealing with probability. Let's just leave it alone. So if I look at number 2, it's looking at the probability of event B, rolling a sum greater than 10 on 2 dice. So capital P, parentheses, capital B, probability of event B. Now, what does that mean in words? That means the probability of rolling a sum greater than 10. So again, rather than going back and looking at the image, I'm going to just take a little snapshot from it, and I have it right here. So how many do I have that have a sum greater than 10? Now be careful here, because 6 and 6 is 12, 5 and 6, and 6 and 5 are both 11. However, when we look at this, 5 and 5 is 10 exactly. So I have to go back to the statement. I want greater than 10. So in this case, if I want the probability of greater than 10, I am not going to count this one. I only have 3 out of my 36. So pay attention to the inequalities. If it says at least 10, a sum of at least 10, then I would count that 5 and 5. So the wording is extremely important. So let's look at part C. Rolling a sum of not greater than 10. So one thing to be aware of is I'm looking at something that's a little bit different. I'm looking at the probability of not B. Well, I know the probability of B. The probability of B was 3 out of 36. So what's probability of not B happening? Well, in this case, we are going to do the idea of 1 minus the probability of event B. If I know that event B is 3 out of 36, the probability of not B happening has to be what we call it, the complement of it. And we're going to look at that notation a little bit later. Is the complement is not the event happening. The notation is to put a in the superscript capital C. So the probability of B complement, which means the probability of not B happening. So if I want to do that, what I'm going to do is I'm going to take 1 minus the probability of event B. So in that case, I'm going to have 33 out of 36. So that takes the idea of a probability model in that all the sums have to add up to 1. And if event B has 3 outcomes out of the 36, not B has 33 outcomes out of the 36. And the notation we're going to come back to a little bit later, but it is important to understand how that's written is B with the superscript of C means complement. All right, so the last one, rolling a sum of 8 or less or a multiple of 4. All right, so that's not event A or event B. So I'm just going to go ahead and write down I have the probability of less than or equal to 8, or I would say a multiple of 4. So this one's going to be a little bit trickier. Let's just kind of figure out what we're going to do. I'm going to use the whole sample space to help me out here. So let's just go first to anything that is less than or equal to 8. And so if I want to find less than or equal to 8, I'm going to find where 8 is. And 8 is right here, 5 and 3, 4 and 4, and so on and so on. So less than or equal to that is going to contain every single one of these. So right now, to make it a little bit easier, what I'm going to do is I'm going to say I don't have any of these. All I have is everything that is here, 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 here. All right, so that's how many have a sum less than or equal to 8. Now we're going to look at the probability of being a multiple of 4. So there were a total of, I look at this, I think I have 10 that I'm not including. There's 36 total. So for the probability of less than or equal to 8, I have 26 out of 36. That's a lot. But I also want to look at or a multiple of 4. So let's see what happens. If I want to look at a multiple of 4, that could be a 3 and a 1, that's 4. I could also have, in this case, a 2 and a 2, a 1 and a 3. Also, a multiple of 4 is going to be 8. So all of these. Also, a multiple of 4 is going to be 12. So how many multiples of 4 do I have? I have 3, I got 5, it looks like I have 9. So there are 9 multiples of 4. But there's an issue. The issue here is of all the multiples of 4, I counted 8 of them twice. If we were to look at the sum of 36, that was every single one of these up in this area. All of these were sums of 36. So the issue that I ran into is, you see I circled, highlighted, I circled this one twice. I circled this one twice, this one twice. All of these are going to be circled twice. So I counted them twice. I can't do that. So I'm going to have to remove some of them that we counted twice. And so I said we counted 3, I got 5, I counted 8 of them twice. So I have to subtract the 8 out of 36, which is going to leave me with 27 out of 36, which should make sense. Because in the original, less than 8, I had, we'll get rid of all these lines that we have, I barricaded it off with that first red boundary. All of those are less than or equal to 8. That was 26 of them. Notice I only added in one more circle outside of that. 26 plus 1, 27. So this is really trying to introduce some of the different ways of looking at probability. And we see in this example, something weird happens sometimes when we're dealing with an OR probability. Maybe we count them more than once, and we somehow need to subtract them. So let's discover a little bit more. To help us understand how to get some of the total events sometimes, there's something called the fundamental counting principle. We can use our diagrams that we had before, our tree diagram, which we're going to cover later, I said. We could also use the fundamental counting principle here called the multiplication counting principle. And what that does allows us to determine the total number of events, the denominator in the probability. So how many different outfits are available for someone with 4 shoes, 3 pants, and 5 shirts? Well, what I can do is I can take the number of shoes times the number of pants times the number of shirts. That's going to tell me how many total different outfits that could exist. So if I were to take 4 times 3 times 5, 60. There are 60 total outfits if you have 4 shoes, 3 pants, and 5 shirts. Now in this one, how many different outcomes are there for a student either hitting their snooze or not? So hitting their snooze or waking up, and arriving on time to their school, which means arriving on time or being late. Now in this case, I'm actually looking at a tree diagram just to kind of show you how it relates. So if we look at this, what we have first is you have the student. And so right here is the student. The student's laying down and the alarm goes off. They are either going to hit the snooze button or they're going to wake up. So that is a total of, you can see, 2 branches there. 2 different outcomes can happen if you either hit the snooze or you go back to sleep. Now if we look at this, there are 2 outcomes after that. They either hit the snooze and they're going to be late to school, or what happens is they're going to hit the snooze and they're going to be on time to school, or they're going to wake up and be late for some reason, or they're going to wake up and be on time. So in this case, if we look, there are a total of 4 different outcomes. And the reason why is because we had 2 branches here and we have 2 branches here. 2 times 2 is 4. So we can use a tree diagram to also help us, and we're going to look at that, like I said, in a different section a little bit deeper. I just wanted to introduce it now to show how it relates to that multiplication counting principle. So a lot of probability so far. Third lesson, we're trying to figure out what are we going to do. And so I want us to focus on what do we already know. And so the last lesson, we looked at simulations, and we saw that they were really good for estimating probability if we do many trials. And it allows us in really complicated scenarios where we might not be able to find a formula to actually go and see the results. And so what I did is I had the screen captures from the NumWorks calculator here where I did a simulation where there's 10 balls, number 1 through 10, they're placed in a bucket, shaken thoroughly, and if I choose 3 at random without replacement, what's the probability of having a sum greater than or equal to 15? And so each one of these is me having the 10 balls in the bucket, reaching in, grabbing one, reach in, grab another, reach in, grab another, record what those numbers are, and then that's trial number 1 right here. Then I do it again, shake it up, mix thoroughly, grab one, grab one, grab one. That's what that one means in without replacement is I'm doing 10 different trials on this. So if I look at this, I want to know what's the probability of having a sum greater than or equal to 15. And this is our simulation. So this is 9 plus 1 plus 3 is 13. This is 13. This is 22. So that is a success. This is 15 exactly. Let's take a look. Greater than or equal to. So I can count that one. That is 4, 1, 2 is 7. This is 16. So this one works. 12 and 5 is 17. That one works. That one's 13. That one does not work. Then 11 and 8 is 19. That one works. 7 and 10 and 5 is 22. That one works. So 1, 2, 3, 4, 5, 6. 6 out of my 10 trials. That's what we did with simulations already. Is we looked at that case of how we can use random integers to help us out. What else we've learned was we learned how to do different sample space. When you have a sample space, what you do is you list off all the possible outcomes. And so I have right down there a scenario. I'm flipping a coin and rolling a die. So if I just want to list them all out, we looked at that with the 2 die with the images. We could also just list them. A heads and a 1, a heads and a 2, etc., all the way to a heads and a 6, a tails 1, tails 2, all the way to tails and a 6. So in this case, there are going to be 12 different outcomes. That should make sense. There are 6 sides on a die. There are 2 sides on a coin. The counting principle, 6 times 2 is 12. Now, each probability, if you're dealing with this, in this case, this probability, all of them have the same probability. They all have a 1 out of 12 chance of occurring. The reason why is because they're all different. Heads and a 1, heads and a 2, and etc. So they all have a different probability of happening. So these are the things we've learned so far with our probability strategies. So now let's look at this activity. This activity, again, taken from Mathematic, when we look at can I draw the same card starburst 2 times in a row. And this game is pretty simple. What you do is we put some starbursts into a bag. Do not worry, we will mix thoroughly. What's going to happen is we are going to reach in the bag and we are going to take out one of the starbursts. So I mix it up, I get in, I get a red. I'm going to replace that starburst back in the bag. I'm going to mix again. I'm going to draw another color. That's red. They matched. That means I win. So that means right now, if I were to keep track, I've won once. And what happens is we are going to do this a total of 10 times per group. And so I'm going to do it again. This is the boring part. Reach in, I get a red, put it back in the bag, reach in again, and what I get is a red, winner, winner. And so I do it again, multiple times. Do not worry. We are going to fast forward this so you don't have to watch me do this many times. All right, so I've done all of them, and I won a total of 6 times. So out of my 10 trials, my 1 simulation that I did, I had 6 victories, which means my percent was 60%. And so what happens is we are going to do this as a class and collect all of the data that we need. So I did this many times. I did a total of 70 times. I did 7 trials with 10 in there. And this is my data. There was 6, 4, 6, 7, 8, 8, 6 victories for each of the groups I did. And that was a total for 45. So out of 70, I had 45 wins out of the 70, which is about 64.3%. And so this is really what's going on with the data. Now what we're going to look at is, based on the result from our group, what is the probability of me winning the game? So really what I'm looking at is right here. Based on just my information. So based on just right here, what is my probability of winning the game? And we calculated that already to be about 60%. So the probability of me winning was about 60%. And that's just for me. So 0.60 was my probability. So we recorded the other groups based on the results from our whole class. What is the probability of winning? This is where I said I had for the whole class. So I'll just say me winning, probability of the class winning. In that case, it was 45 out of 70, which I said was about 0. I believe it was a 643 is what we had. Now, that's the class. And so really you can see it's different than mine because mine is a one-time thing. We did it many, many times, not quite many, many times. We did it a total of 7 times. I guess that's not a lot. But man, if we could do it many, 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 many times, that would give us a better idea of what the true probability of this event is going to be. And that's really what question 3 is asking us. How could we do this better? I only did it 7. What if I did it 700 times? And in that case, I'm going to get closer and closer and closer to the true probability of winning that game. That is really what the law of large numbers represents, is if we do it many, many, many times, we are going to get closer and closer to the true probability that we're looking for, to understanding them. So that is the first part of the activity. So we have here an actual table that outlines all the possible outcomes. So you can see actually what was in that bag. What was in that bag were 4 red starbursts and 2 yellow starbursts. So I would draw one of them, and then I would replace it and draw another. So there was always 4 red and 2 yellow starbursts in that bag. And we're asked to complete this table. And the reason why is because question 5 is asking us the different probabilities for all the outcomes. And so I can, in this case, I didn't know it was in the back in the beginning, but now I know I can actually outline and figure out what's the true probability of me winning this game. And so what I'm going to do is I'm going to list them all out. I can draw a red and a red. If I look at it, a total of, I think it's going to be 4 by 4 in this case, which would be 16 ways for me to draw 2 reds. So that would be 16 ways of winning. But also remember, they just had to match. So that means I could draw a yellow and a yellow as well. As long as they match, that way allows me to win. So in this case, I see 16 and I see 4, that there were 20 different ways of me winning total. If I look at the first problem, what's the probability of me winning with 2 red? Well, in that case, I have, looks like just the 16, let's get rid of the rest of these, out of the, how many total? Well, it's 6 by 6, so it looks like it's going to be 36. So there is a way for me to win. There is 16 out of 36. Look at the notation there. The probability of the first candy being red and the second candy being red. So you can see here that there's a new word there, the word and. 16 of them out of the 36 allows me to win with just 2 reds. So that's this area right here. How many with 2 yellows? We already talked about that. That would be 4 out of the 36. So the probability of the first being yellow and the second being yellow is 4 out of 36, 0.111. What is the overall probability? So I've already counted that. That was the first thing I did. Is, oh, we had 16 and we had 4, that was 20. So in this case, what I can do is the probability of me winning is I can add those 2 probabilities together. That's the concept with probability we're looking for is there's an event A, 2 reds being drawn. There's an event B, 2 yellows being drawn. That's how I win. So what's the probability of me winning total? Event A plus event B. So 16 out of 36 plus 4 out of 36 is going to be 20 out of 36, or 0.555555, 0.556. So that is the event. Now, what's probably of me not winning? Well, again, if I have the diagram, I could count right there. And it looks like I have a section of 8 right close to me, and then over on the far side down there, I have another section of 8. I'm thinking it's going to be 16 out of 36 because I can look at the picture. But the reason why we're saying this is because it says the word not. And not winning, we introduced this a little bit before, is the complement. So we have here the probability of not winning. I can call that the probability of winning and then put in the superscript a capital C. That's the complement of it. And to do the complement, you do 1 minus the probability of it happening. So I did 1 minus the probability of winning, which is 16 out of 36, which is 0.44444. So this was the Starburst activity. The main purpose behind it is for us to understand how to outline a sample space. And the hidden thing you're trying to look at is the different ways of dealing with probability. What does and really mean? It looks like it's the intersection of that first candy and the second candy in the table. That's important to keep in mind in the future. What does it mean for combining probabilities? You know, I'm winning with 2 reds, 16 out of 36, winning with 2 yellows, 4 out of 36. Well, how do I win total? I could either have 2 reds, or I could have 4 yellows. Sorry, 2 yellows, 4 total. So that would be the adding them together. So there's the first part of it. Now that we all have that written down and we understand what's going on, let's actually go for the concepts that we're trying to learn. Sample space. Sample space is a list of all possible outcomes. You're going to see all the different events that we're dealing with here. The probability of an event is going to be the number of outcomes of event E over the total number of outcomes there. So how many times did event E happen out of the total number of possibilities that there could be? When you're looking at this, you have to realize all outcomes must have an equal likely chance of going through. We must have the randomization happening there. What happens is that also means, we go back to the starburst activity, notice there's 36 total squares there. Each one of those squares has a 1 out of 36 of being selected. That's what that's referring to in that part of the concepts. Legitimate probability model. You kind of heard me talk about this before, is all the probabilities must add up to 1 in the sample space. And we already learned that each probability has to be between 0 and 1. Probability is a decimal between 0 and 1%, or between 0% and 100%, but probability is between 0 and 1. So rules and notation, this is the big part. This is the part we're trying to introduce during the video a little bit, and we're going to get more comfortable with in future lessons as well. Complement was discussed. That is the probability of an event not happening. The way that works is you do 1 minus the probability of the event happening. And so you can see down there I have a Venn diagram. That diagram actually allows us to look at, here is every possible event that could happen. Inside that square is everything. That would be a sum of 1. That entire square has an area inside of it as 1. Here's event A. If I want to find the probability of not A, this area here, I can do 1 minus the probability of A. So that was the idea of complement. Then we looked at 2 different words. We looked at probability of an event A and B, or we looked at probability of event A or B. When it was and, both of them had to happen. The first starburst had to be red, and the second starburst had to be red. Or the first starburst had to be yellow, and the second starburst had to be yellow. So in that case, we use this notation of, you would call it an upside down U. This symbol right here means and. And we're looking at another way of helping us remember that. You could also see that it's kind of like well, it kind of looks like if I put a little bar right here, that kind of looks like the letter A, doesn't it? So we can see A and, that is and. That's the probability of both events occurring. Or is the probability of one or the other event occurring, or both events occurring. It's got to be A or B, or it could be both A and B. So we look at this, we want to make sure that it has a notation. That one, well, that one's the upside down of the other one, isn't it? You would call it a capital U. Just thinking about this yesterday because I get bored and I think about mathematics. When you look at this, it's kind of like, if I think about this, it's the word or, which maybe we misspelled it like O-A-R, oars on a boat. And this looks like it could float in water, kind of like a boat. And so oars are going to be that direction. So ands are the upside down U, oars are the U, and those are the different notations that we're going to use. It's kind of expected on the assignments. So let's go look at some of the practice problems. Pew Research Center reported that family size is shrinking. Oh no. Suppose we are to randomly select one mother and record the number of children. There's a probability model down there for us. Now Stephen, he argues that this probability of a mother having exactly 2 children is 1/4. And he's saying that because there's 4 categories here. There's either 1, 2, 3, or 4 more children. So he's thinking that each one has a chance of 25. And we can see in that table he's wrong. Now the reason why this is wrong is because they don't all have the same likelihood of occurring. All the probabilities are different. Though there's 4 categories in this case, those 4 categories all have a different probability assigned to them. So it's not a 0.25 probability of them happening or a 25% chance of each category happening. So that's Stephen's argument, is this idea of he's looking at categories and going, oh, that means they all have the same likelihood. Not the case here. Now find the probability of having exactly 2 children. Show your work. And now in that case, I need to use the idea of what a legitimate probability model is. I'm going to take and realize that whole table in that probability should add up to 1. So I'm going to take my 0.22 plus my 0.24 plus my 0.13. I'm going to add them together, and then I'm going to subtract that from 1. And so there is a 0.41 probability of having exactly 2 children. So there's a gap in the table. I can use my legitimate probability model definition that the probabilities all have to add up to 1 and find that missing table cell. And so we can now use that to answer the next 3 questions. And you can see I put in there 0.41 in the table. Find the probability that a randomly selected mother has less than 2 children. I should read the directions. Using proper notation, showing my work, and finding the answer, of course. So if I want to do that, let's use the notation. So the notation would be the different ways I'm using the capital P, the parentheses, and if I needed the and or the or as well. So less than 2 children. I didn't define that as an event, so I'm just going to say the probability less than 2 children. Less than 2, by the way, we need to be a little bit careful with. Another way of saying less than 2, if I kind of draw it on here, less than 2 does not include 2. It's only to the left of it. So another way of me saying that is the probability of just 1 child. So in that case, the answer is 0.22. So one thing that's nice sometimes, if you list them out, you can actually draw in the boundary and point in the direction of where you want to add your work. So let's get rid of that for the next one. Maybe I can do it again here. Find the probability of randomly selecting 1 or 2 children. Now I know, like I said, you could just go, sweet, I'm going to add these together, but wait a minute. Using proper notation and showing your work. Darn. So find the probability that a randomly selected mother has 1 or 2 children. So the probability of 1 or 2. Look at that notation. You see that word or, and look at that boat just floating right there. So we have 1 or 2. And in that case, it's 1 child or 2 children. I'm going to add the probability of 1 and add the probability of 2. That is where we got the 0.22 plus the 0.41, which would give me a 0.63 probability. The main notation I want us to remember is that this symbol means or, and that tells us that we are going to add all the different outcomes. So find the probability that the mother does not have 4 more children. So hold on, let's take a look. Let me get rid of what I have here already. All right, so does not. That word not sticks out to me. That word not, that's telling me complement. It's not happening. So I could, and especially with a small probability model like this one, not 4 more children means 1, 2, or 3. I could add those because there's only 3 of them together, but I want to work on notation. So we're going to do this. The probability of not 4 children is the probability of 4 more children, is 4 more children complement. That's the notation we're looking at. That means not 4 more children. So we want to focus on this idea of using a capital C, meaning complement, which is that idea of 1 minus the event actually happening. So 1 minus the probability of 4 more children would be 1 minus 0.13, which is going to be 0.87. So this is a very good understanding of a legitimate probability model. You look at the table, it's pretty straightforward with the table, but what we want to do is we want to focus on the notation. We want to focus on how it works, because where we're going, it's extremely important we understand that. So let's go on to the next one. According to the American Heart Association, AHA, try saying that 3 times fast, is 16% of adults had high cholesterol. That's 240 or above. If you look at it, 29% have borderline high cholesterol of 200 to 249. A is the event of a person having high cholesterol, so we're defining the variable. That makes writing a lot easier. B is the event of a person having borderline high cholesterol. Now we'll do part 1 first. Find the probability of A, superscript C. What does that mean? Complement. Find the probability of A complement. That is the probability of event A not happening. So we're going to pay attention to notation here. That says 1 minus then the probability of event A actually happening. So if I want to find the complement of A, I do 1 minus A, so 1 minus 0.16, and that is 0.84. That is the probability of A complement. Now, I want to apologize on the I and the II. I, for some reason, changed to blood pressure instead of cholesterol. So we're going to focus on just the concept that matters. Explain why this does not represent the probability of an individual with normal to below normal cholesterol levels. Why doesn't it? I mean, if A is the probability of somebody having high cholesterol, A complement is the probability of somebody not having high cholesterol. So why does this not represent somebody having normal to below normal cholesterol levels? And it's really because of event B. If I were to make a little picture to help me out with this one, is I could have below normal cholesterol level, normal cholesterol level. Event B said borderline high cholesterol. Event A was high cholesterol. So when we found the probability of A complement, what that did was it did find the probability of someone with below normal or normal cholesterol levels, but it also included event B. So that is kind of a trick idea, is it represents those without high cholesterol, but that's people with normal to below normal, which is good, but that also contains event B as well. Those who have borderline high cholesterol. So the question is, how do we find the probability of somebody with normal to below normal cholesterol level? So in other words, let's go back to this picture. I want to actually know the probability of these people down here, those with normal to below normal cholesterol level. How do I do that? Complement. Complements can help in because I don't know those values, but I do know they all add up to 1. And if they all add up to 1, I could take these two, add them together, subtract it from 1. And that would give me the information. And that's what we're actually doing. I'm going to take the probability of event A, the probability of event B, combine them together, and subtract from 1. And so in that case, when I go through it, I'm going to get 1 minus 0.45, which is 0.55. So this is an interesting way of looking at complement. I can do the complement of, in that case, 2 events. And what did I do? I didn't just look at the numbers up there in the top. I didn't just focus on the 0.16 and the 0.29. I visualized it. I kind of drew an outline of what it was, and that really made it easier for me to see probability. Sometimes when you list them all out like that, it's going to make your life easier to see visually how to get the calculations. So let's move on to the next part, which is a blank screen. So therefore, we are done. That is lesson 5.2a. It's a lot of stuff, but like I said, the main thing you can see is we're focusing on introducing probability as we go through. Hope you enjoyed the lesson.